Good morning, everyone. My name is Anirvan Gupta, and today we are going to discuss a very important topic in the field of physics, and that is oscillations. So, this forms a part of your undergraduate second year course of the University of Pune, SPPU, and this is one of the most important topics that you would actually go through when you go even for your higher studies, right? So, oscillations. The first thing is what comes to our mind when we talk about oscillations. Okay, what is the first thing that would come to our mind? And you would say that you have an object or a particle which moves from one point to some other point and then retraces the positions back. Okay, so there is an object, it moves, the position changes, okay, with time along some path, and again with time it retraces the same positions back, it retraces the same path back. So this to and fro motion that an object is undergoing is called as oscillations, in simple words, right? Now there are many oscillations that we see in our daily life. We come across many objects which are oscillating. A very simple example, I like to give a demo. A very simple example, okay, a pendulum, a simple pendulum rather. Now this is a household pendulum because I do not have access to labs here. So I hope you can see that a simple pendulum, there's a string and there's a mass which is attached to this string, right? So if it is displaced, then what happens? The pendulum moves, and we say that the pendulum oscillates. So it goes to one position, okay, there is one position, then another position. With time the change in, there is a change in the position of this mass. Okay, when we are using pendulum, most of the time we call this a bob. All right, there is a mass, a spherical mass which is attached, and that is called as a bob. Here we have a normal mass. Okay, so the position changes, the position changes, and it goes to one extreme and then retraces the all the positions back to the first or the initial position. So that is what we say, and then we say that the pendulum is oscillating. All right, so there is a string and the position of the mass, the position of this mass which is attached, it changes with time. Okay, as a function of time it changes, and that is simple pendulum. There are many more oscillations that you would also see in objects in your laboratories. Like if you visit your mechanics division of the laboratory, you would have many springs which are there, right? So you have a spring, suppose I have a spring which is fixed to a rigid support and vertically it is hung. So there is a mass which is attached. Okay, some mass is attached to the spring. So if I pull the spring, what would happen? If I pull it gently and release it, then what would happen? The mass would move up and down along with the spring. Along this vertical, the mass would move up and down. So it would retrace some path. It would go to this point, okay, some extreme, then it would come to some other extreme at the lower end, and then it would continue, right? That is again oscillation of the spring mass system, we call it. Similarly, if I have a spring which is attached to a horizontal path, if you have a horizontal path and there is a spring with a mass which is attached, and then I move this mass either to the right and I release it, then the mass would again perform oscillation. Okay, so the spring mass system, it goes to the left, it goes to the right, and it retraces that path. Okay, that is also one kind of oscillations. Well, several other objects that you see in your day-to-day life can give you demonstration of what an oscillation looks like. Another simple example, if you can see this light bulb. This is a light bulb, a simple light bulb, and I place it on a platform. All right, I place it on a platform. I hope that is visible. All right, okay, and I gently push it on one side. What you would see, it would move here and there, here. I do not move this platform like this, but the bulb, because there is a filament, there is some weight, it is moving here and there, right? That is again some demonstration of oscillation. Another very interesting demonstration of oscillation, let me show you. I have a beaker which is filled with water, okay, partially filled, and there is this glass bottle, a simple glass bottle that I am having. Okay, now I dip this glass bottle in the beaker, then what would happen? Just let us see. let us see this. If I dip this, what is happening? It is floating in water, right? It is floating there, you can see that. Now if I gently push it, see, then it would go down, go up, go down, go up, right? So if I gently push it, what is happening? There is some kind of oscillations. 1 second, okay, see, there is this bottle. I hope that is visible. All right. Yeah, there is the bottle, right? I gently push it. See, it's going up and down, up and down. You see that? Okay, because it's going up and down. And interestingly, there are two types of oscillations that you see here. One, the bottle is going up, down. Second, the bottle is going up, down. That is one. Second, the bottle is also moving this way. So there is an angular oscillation that you see here, right? So there is one oscillation which is up, down, one oscillation which is sideways. So again, there is a combination of different types of oscillations that we see here, right? So various systems are there in your day-to-day life. You can see them oscillating. Now, oscillation is a phenomena which is not related only to material objects which are moving. Okay, material objects in motion. It is not only limited or restricted to those objects. For example, you can have oscillations of electric field. You can have oscillations of magnetic field. So what happens in this case? Like if you have magnetic field, the magnetic field, it changes between two extreme values. It has one value, it has another value, and it changes between those two values as a function of time. So that is what is the the oscillations of magnetic field. For example, the light that we see, electromagnetic waves, let us say the light coming from sun, what is it made up of? Electromagnetic waves, electric and magnetic field. So in that case, the electric and magnetic field, they oscillate with a very high frequency of the order of 10 raised to 15 times per second. So that's a large frequency, and there also both the electric and the magnetic field, they change as a function of time. They go to one value, they go to another value, and then keeps on moving between these two values. So they are functions of time, and they have a very high frequency, right? So everything, there are so many things around us that you find to be oscillating. Okay, a very simple example, the pendulum of your clock, again a mechanical system. If you have seen a pendulum, okay, of a clock, it moves. Okay, it moves tick tick tick, and its time period is 1 second. It moves every 1 second, right? You can calculate the frequency from that, right? Now oscillations, as we said, it is not restricted only to mechanical objects in motion. You can have oscillations of very abstract quantities. For example, if you take some trigonometric values, like if you have sine of x. So how do you plot sine of x? If you have x is changing, okay, if you have x is changing, then how do you plot sine of x? The graph, it goes, okay, something like this. It looks like this, right? So the value of sine of x, it fluctuates, or it varies between two extremes. What are that? +1 and -1. So as your x increases, the sine, it goes to +1. Then again, as x increases, it goes to -1. If you further increase x, again it goes to +1, again it comes to -1. So that is oscillations of your abstract quantities like sine x. Similarly, you have oscillations of cosine x, tan x, all these trigonometric functions, right? So again, oscillation is not something which is restricted only to material objects in motion, right? You can have oscillations of several quantities. Okay. Now, when we are talking about oscillations, having known the brief about oscillations, what is the mathematics behind that? Simple one, right? You write ma equal to minus kx. That is the governing equation. And from Newton's laws, we know that what is ma? Ma is nothing but the force which is acting on a moving object. Okay, it is active. X is the position of the object, m is the mass of that body or object, a is its acceleration, and k is some proportionality constant. There is a significance of this minus sign, which we will discuss very shortly. Now we are talking in with reference to an object whose mass is m, okay, and moving with an acceleration a. That is, we are talking about such an object. So you know ma, that is already the force, and therefore kx should also be the force. And what is this force called? This force is called as the restoring force in the context of oscillations. It is called as the restoring force. What do you mean by restore? Now see, when your pendulum, suppose we again take the example of a pendulum. If the pendulum is here, this is called as the point of stable equilibrium, where the pendulum is not oscillating or where it is not moving. The mass is fixed, okay, it is not moving. Now if I just displace it, then what happens? You see, it oscillates, right? But if we pay attention, if I am displacing it towards my right hand side, then there would be a force which is again taking it to the point of equilibrium. Now because of the energy that it possesses, it goes to another extreme, right? And there is a force which is again bringing it back to a point of equilibrium. So if the force is this way, if the displacement of the pendulum is this way, the force would be acting in the opposite direction. If the displacement is this way, the force will act in this direction. So there is a force which is always acting on the oscillating body, and this force is in a direction which is opposite to the displacement of the oscillator or the body which is oscillating. So therefore these forces are called as restoring force. They are trying to restore the point of equilibrium, the point of stable equilibrium. They are trying to restore it. Now from the laws of calculus, if you have m into a equal to minus kx, okay, if you know the position and you know that it is a function of time, the position is changing with time, you can find the velocity of this oscillator to be d dt of x. And having known the velocity, you can find the acceleration of this to be d dt of v. Right, these are from the laws of calculus. You know one quantity, you take the time derivative and find some other quantity. So if you apply these values, if you use these values in this basic equation, then what you would have? I would have m, in place of a, I can write dv by dt, v is further dx by dt. Simple mathematics, I write it as d2x by dt square, right, equal to minus kx, or I can write d2x by dt square equal to minus k upon m into x, and that k upon m, let me write it as omega square. And there is a significance of this squared term. Why don't I write it as omega? We'll see this in some other lecture. Okay, so d2x by dt square equal to minus omega squared x. So this is the basic equation of oscillations that you could have. And d2x by dt square, it gives you the acceleration of the oscillator. So acceleration is given by minus omega square x, right? So this is the basic governing equation. Now if there is an object, which satisfies this equation, let us call it as equation 1. If we have an object which is moving and its motion is governed by this equation, then we say that the object is oscillating. And how do we give this value of x, that is the position, as a function of time? It is given by, let me write it in simple terms, a cos of omega t. We can write it as a sine of omega t or a cos omega t plus phi, sine omega t plus phi. Let us keep this simple as of now. So x equal to a cos omega t. So if you have an object which is following this equation 1, then you say that the object is in motion. And if the object is in motion, it is oscillating, okay, if the object is oscillating, then the value of x, the position, would depend on time, and that will be given by this expression. What will be the dependence of position on time? It will be given by x equal to a cos omega t, right? I hope that is clear. So x equal to a cos omega t. Now if you look at this expression very closely, that is how the position depends on time, you would see that a is a constant which is called as the amplitude. A is a constant which is called as the amplitude, right? And this doesn't change. And therefore, if cos omega t goes to its extreme limits. So what are the limits of cos? You have +1 to -1. Okay, cos goes between +1 and -1, just like sine. So x would vary. If cos omega t is +1, this x would be given by +a, and if cos omega t is -1, this x would be given by -a. So the amplitude of oscillation, it varies between +a and -a. In other words, the magnitude of this amplitude doesn't change. It remains constant. So the amplitude of oscillations of a body does not change if it is following this expression. However, in real life, you do not have any object whose amplitude of oscillation doesn't change. It has to change with time. Rather, it has to decrease. For example, if I again consider this simple pendulum, if I oscillate it, what you would see? With time, the amplitude, that is the maximum displacement that this pendulum is showing, this is going on reducing, right? It reduces with time. As time passes, as time increases, time can always increase. You cannot bring back time. You cannot go back in time. So it is, right, reducing. So this is an ideal situation, but it is not very practical, or it is not real. So how do you make this real? You add another term to this. Expression. So when we are writing this basic expression for acceleration of the body, okay, rather if I am writing the force, I'll write it as m into a. So m into d2x by dt square equal to minus kx. That is the first expression that we had written. So there is another additional term that I would add here, and that term would be given by b, okay, into v. B is again some constant into v, that is velocity. So these forces, okay, because of which the amplitude of oscillation decreases, there are dissipative forces. These are called as dissipative. So if you have this simple pendulum, what are these dissipative forces? You can think of the air drag. There is a air resistance to this motion. There is some friction. If I am just tying it somewhere, or I am suspending it somewhere, there will be friction between the surfaces and this thread. So these forces tend to decrease the amplitude. These are frictional forces. So it is observed that these forces are generally proportional to the velocity. Right? So it is given by minus of b into v, where v is the velocity of the oscillator, dx by dt. Right? So if you add this term, what is happening? After a certain amount of time, the oscillator would come to rest. So how would x change? X, which was earlier written to be cos omega t, you would have we are not deriving this, you have an additional term here, e raised to minus some constant beta into t. Now because of this exponentially decaying term, what would happen? Your amplitude of oscillation would exponentially decay. So how can you write this expression? This expression can be written as a e raised to minus beta t into cos omega t. So this term is the amplitude, which is exponentially decay. Although a is constant, as time increases, as you increase t, when t is 0, e raised to minus 0, that would be 1. So it would be a cos omega t, and that is the case of the first case, that is undamped motion. The amplitude of oscillation doesn't change, a cos omega t. But if you have this expression, as t increases, this term exponentially, gradually it decreases. So what would be the nature of this x? So if I am having x, with respect to t I am plotting, okay, what would be the nature? The total amplitude would be exponentially decaying. And how would this curve look like? This curve would look like something like this, because the cosine term is there. So this nature would be there. Okay, rather I would have the arrow here. Okay, so this nature would be there because the cosine term is there. But the amplitude, the maximum amplitude here, it was maximum, then it is decaying, then it is decaying at several time intervals, it is decaying, right? So this kind of motion is called as damped harmonic motion. It is called as damped harmonic motion. Damping means the amplitude is reducing with time. That is what we mean by damping. Now let us see another. So this is one. We have seen one where your amplitude doesn't decrease, x equal to a cos omega t. We have another case where your amplitude decreases, that is the damping forces are there, dissipative forces are there, and that is a cos omega t e raised to minus beta t. Now if you provide some external force to the oscillator so that its amplitude doesn't decrease, right now whatever is happening on its own. Either the oscillator is moving, ideal condition, or the amplitude is decaying. If you provide some external force which itself is periodic, which itself is oscillatory, then let us see what would happen, and we'll see this very quickly. If you apply some external force, and I would like to give you a demonstration if that would be possible. Okay. So I have here again a homemade stand. This is a pencil stand, simple. I have taken it to be a stand because I wanted to use these grooves, these holes there. And this is a simple plastic broomstick. I have simply joined it, nothing very fantastic about it, but I have simply joined it end to end so as to make it long so that the oscillations can be large. Unfortunately this area is very small where I can show. Now there will be two conditions, okay, three conditions rather. I will give some force to this stand, okay, some periodic force. What do you mean by periodic force? It would oscillate, okay. So this is how it would oscillate. You get that? This is how it would oscillate. So I would apply three frequencies. One, a very slow frequency of oscillation where it is rate of change of position is very small. One will be very fast oscillation, okay, very fast it is moving. The third would be intermediate oscillations, okay. I have to take this away because otherwise you cannot see this tip, okay. This tip has to be seen, I believe. So what would happen in these cases, three cases? Just focus, let us focus on this tip, on how this stick is moving. Please focus on this. I hope I can do a little justice while doing it. So here I am moving it very slowly. Focus on the tip, how much it is moving. Okay, how much it is moving. From where to where. You can see how the tip is moving. Okay. This is slow, a very slow frequency I am giving. Okay, very slow frequency. Now I move it very fast. Focus on the tip. I move it very fast. Focus on the tip. How much it is displaced? Very little amount. Now if I give an intermediate frequency, this is an see how the tip is moving. See that? It's showing so much of amplitude. Okay, it's now again fast. Again fast. See how the tip is moving. Again slow. See how the tip is moving. And now intermediate. See how much it is moving. So what we see between these two frequency extremes that we are applying, a slow moving, okay, what is happening? The frequency that I am giving from my fingers, I am giving some force. So this frequency, okay, when it is very slow, the amplitude of oscillation is very low, okay, very little amplitude. When this frequency is fast enough, the amplitude is again very small. But when this frequency is intermediate between these two, the amplitude is huge, the amplitude. So what is happening? The frequency or the force that I am giving using this stand, the frequency that I am giving using my fingers, when this frequency matches with the natural frequency of this broomstick, then it oscillates with maximum amplitude, okay. So naturally at some intermediate frequency there is a frequency match and its amplitude of oscillation becomes maximum, and that condition is called as resonance. A very simple example of resonance most of you would have seen at your homes. All of you have washing machines at your homes. Sometimes you would see that the washing machine vibrates vigorously, gad, some kind of sound it emits, right? Why that happens? Because the force that we are giving to the washing machine from this electrical signal, there is some frequency of the signal, right? Whenever this frequency that we are applying, it matches with the natural frequency of this drum, of your machine, then the machine starts vibrating with a maximum amplitude. And you would observe this while you switch on the machine or you switch off the machine. Generally you would see that in the intermediate stages, no, because it is already, the frequency, there is a match, okay, and when it starts rotating, it's already in progress. So when you switch on, it slowly starts rotating, right? So there is some frequency, of that, and there is a point at which the frequency matches with this external frequency that we apply. So at that time you would have this very large vibrations or amplitude of vibrations. Alright, so this force that we are applying, you saw this force that I am applying. Alright, this force is external and periodic. It is changing with time. It is following the same path, 1 2 1 2 1 2, right? So it is periodic again. So this force is given by some value F0. This force is given by some value F0 cos omega dash t, let us write. Okay, F0 is some amplitude of that force, and omega cos omega dash t show that it is again periodic. So you would have m into d2x by dt square. We had these two terms, minus kx minus bv plus f0 cos omega t. Alright, now this one doesn't really follow cos omega t, but it is good to give a demonstration. Okay, it is not really cos omega t here, but for demonstration purpose that would suffice. So now you have this 2, right? So if you find out x, you had this earlier x, a cos omega t, and now you can have another displacement given by cos omega dash t. Okay, because of this force that we are applying. So whenever this omega matches with this omega dash, you say that there is a frequency match. This is the original frequency, or you call this as the natural frequency. Okay, it is given by upon 2 pi, that is, but this is frequency is good. Okay, so this is natural frequency matches to the applied frequency, then you would have maximum amplitude of vibrations or oscillations, and this phenomenon is known as resonance. Okay, this phenomenon is known as resonance, and all the oscillations that we get because of this applied force F0 cos omega dash t are known as forced oscillations. So we have seen what are undamped oscillation, where your amplitude remains the same, what are damped oscillations, and what are forced oscillations, right? So more mathematics, more discussions on these terms we would see in some other class. I hope you enjoyed the lecture. Thank you so much and have a nice day.